Hello, welcome back. So in the previous video I had shown you how to refer to these notes and how to use the different linking structure in this document to jump to different topics. And also we had seen the introduction to gears. In this video we'll be continuing to see the classification of gears. So let's proceed. So here you can see the types of gears have been mentioned. So broadly, if you see the types of gears, they have been divided into three broad categories. So the first is the parallel shafts, if the gears have the parallel shafts. The second type is intersecting shafts, if the shafts without being parallel, if they are actually intersecting. And third are skew shafts. Skew shafts are those wherein suppose the two axes are neither intersecting nor parallel, then these type of axes, they're called skew. And the gears which are mounted on these, their shafts are called as skew shafts. So first of all, let us go to the parallel shafts and see these four types of gears that we have as part of that. So let's proceed. So here we can see the parallel shafts. In that, the first type of gear is the spur gear. On the left you can see an actual image of the component, what the components look like. There may be slight variations in that the gears are always designed in such a way to reduce the total amount of weight and at the same time retaining maximum power, maximum strength. And that's the main reason because of which you can see here in the middle there is some material which is removed. The larger gear is actually called as the spur gear and the smaller one is called as the pinion. The smaller gear is usually the one which is the driving gear. It receives power from the different source. The source may be an engine or a motor, and that power is transmitted to usually the larger gears, because what happens here is we have to reduce the velocity, and the velocity ratio is going to be less, which will significantly increase the torque transmitted. And that is the main reason why the pinion is usually the driving gear, and it will transmit the power to higher gears. So this component you cannot draw in exam cities. So when you need to draw the diagrams, you can use this diagram here, which is a sketch. You need not mention all these terminologies. You just have to draw a part of the circle with a few teeth which are meshing with each other. That should do the trick. There are some additional points mentioned here, like the module of the two meshing gears has to be same. Module is the ratio of diameter to the number of teeth, and this module value has to be the same for the two meshing gears that we are seeing. If the module is not the same, then the teeth is going to be of different sizes and there will be meshing problem. So when you are choosing two gears which you want to mesh, make sure that the module is same. Then there is no actual thrust. The actual thrust is the thrust, that means the force in the direction parallel to the axis. This doesn't exist in the spur gears. It actually exists in the helical gears, which we have next in line. We'll see it later. Contact of teeth is along a tooth width and parallel to the rotational axis, and the loads are applied suddenly with impact, and this introduces high stresses and there's a lot of noise. And this is the main reason why we cannot use these gears for taking up high amount of loads and at higher velocities, and also for higher velocity ratios. This can only be used for lesser loads at slow speeds. Next, coming to the spur rack and pinion. This is a slight variation. You can say it is a special case of this spur gear and pinion, in that if you go on increasing the radius of this larger gear, the spur gear, when the radius becomes infinite, that basically transforms it into a straight line, which is called as the rack. You can see on the right side this is mentioned as rack. And the rack, while the rack moves to and fro, left and right, the pinion is going to move around. So this kind of mechanism is also used at various places when you want to convert the rotational motion into to and fro motion. There are some additional points mentioned here. You can just go through them. Then we have something called helical spur gears. You can just call them helical gears as well. Here the teeth are slightly curved. So in case of spur gears, we had seen that the teeth profile was extruded parallel to the shaft, whereas here there is going to be a small angle with the shaft. You can see here in this diagram the teeth are slightly inclined here, and the angle of that is called as the helix angle. So you can see here that the helix angle here is alpha. So if you want the two power to be transmitted alongside parallel shafts, you have to ensure that not only the model of the two gears is the same, but also the helix angle has got to be the same. Now when we come to the helical gears, because the teeth are slightly inclined, instead of line contact there is going to be just point contact which will travel alongside those helical teeth, and the load application is going to be gradual. That means we can operate these gears at much higher velocities, and also higher velocity ratio is possible, and they can take up much larger weights, larger loads as well when compared to the spur gears. So you can see here the point is mentioned, speed ratio can go up to around 10. Whereas these gears, they also have a big disadvantage. The biggest disadvantage with the helical gears is the side thrust. Side thrust means each gear is going to experience a force which tries to displace it, tries to slide it parallel to the shaft. So while the upper gear, you can say it moves to the left, the lower gear tries to move to the right. That means after some time, if you are not ensuring that the gears are not properly placed with some collar construction or something like that, then there is always a chance that the gears will slide on the opposite sides and disengage. So this is a very big problem, and to solve this problem, that's where the fourth type of gear is coming into action, that is called as the double helical gear. So what we are doing here is we are placing two opposite type of gears side by side, so that whatever side thrust is created by one set of gear, it's going to be cancelled by the other. And special type of this double helical gear is called as the herringbone gear. Herringbone gear and double helical teeth, they are not much different. There's a very small difference between these two. You can see here, when you see the double helical gear, there's a small groove separating the two gears from each other. Of course, the two gears cannot move independently, they are welded together very strongly. But there is this small groove, which means the teeth are not exactly coming into contact with each other. Whereas the herringbone gear teeth, here there is no such groove present in the middle. I can actually show you an actual part, a gear part as well. You can see here in the middle, the teeth are actually meeting each other, so there is no groove at the middle. And that's what is a small difference between herringbone gear and double helical gear. Herringbone gear is actually a special case, you can see, of the double helical gear. Now moving on to the next type, we have the intersecting shafts. In the intersecting shafts, the gears are going to be placed like this. They are called as the bevel gears. And instead of having the pitch cylinders that we saw in the previous case, in the case of the spur gears, what we have here are pitch cones. So you can see here this line and this line at the bottom. These two lines, they form a cone that envelopes the one of the bevel gears, and these two lines, they form a cone which defines the bottom gear. And the two pitch cones, when they are having a line contact with each other, when one cone is made to rotate at about one axis, it's actually going to drive the second case by way of friction. And similar to the previous case, the friction is not sufficient to make positive transmission of torque take place, and that's the reason why we are putting all these teeth over the bevel gears. And there are some additional points that we need to take care of when we are talking about the bevel gears. In this particular first type, we have the straight bevel gears, in which the teeth are actually straight. But you can see the cross section that we have of each teeth, it's slightly narrower at the top, and when it is coming down to the last bottom, the cross section is expanding. That means it is slightly wider at the bottom. So this is the primary difference that you need to keep in mind when you're talking about the straight bevel gears. So some additional points, let us see what they are. The cross section of the teeth vary throughout the length, narrow at the top and wider at the bottom, as I said. The contact between the teeth is a straight line, and of course, similar to the spur gears, there are going to be high stresses because the loading is going to be sudden impact loading, and they're going to make a lot of noise. Because of this very reason, they have to be operated at low speeds, and also you cannot load them very highly. We should also keep in mind that if we are using two identical bevel gears for connecting to perpendicular shafts, this particular type of gears are called meter gears. And internal bevel gears are also possible, he's saying, but I have not seen these internal bevel gears at any point. You can just consider that as a possibility at this particular time. Coming to the next type of gears, apart from the straight bevel gears, we have something called the spiral bevel gears. Spiral bevel gears are slightly similar to helical bevel gears when we are talking about the parallel shafts, whereas here there's a big difference. The difference being that instead of having straight inclined teeth, here actually there's a radius. You can see the teeth that we see here, they're slightly radial. That means they are the curve that defines the teeth that is circular instead of being a straight line, and that is a very big difference compared to helical gears. Now coming to the points, of course they are much smoother and quieter because there's going to be just a point contact, and they can be operated at much higher speeds, and the velocity ratio can be high, and they can of course take a lot of load as well. And because of this very reason, nowadays we are using more and more of these spiral gears in most of our vehicles. And you can see the last point here mentions this is used in the differential of an automobile. Differential, of course, you'll be learning more about that in the dynamics of machines, which we'll have next semester. Coming to the Zirol bevel gear, this is the third kind of bevel gear, which is almost more like a hybrid between the straight cut teeth and the spiral teeth. You can see here the difference has been shown with this help of the three diagrams. Straight teeth is the first diagram, spiral teeth are shown here. The second diagram, you can see there is the path of the teeth is along a circle. Here in the Zirol teeth, of course, you can see the path is along the circular, but the radial line that you see, the beginning of the teeth and end of the teeth, they are happening on the same line which is coming from the center. That is not the case in the spiral teeth. So Zirol teeth, that's why I'm telling you that it's a hybrid between the straight teeth and the spiral teeth. It has advantages of both straight teeth and the spiral teeth. The points I mentioned here, you can just go through them and make sure you're able to write them in the exams the same way. Coming to the skew shafts. Skew shafts, as I told you in the beginning itself, these are shafts which are neither parallel nor intersecting. So these kind of shafts are very very difficult to operate, and for this particular case we're using a hyperboloid type of gears. Now a hyperboloid is a shape that you must have seen in the spiral kind of sitting stools that is carried out by the pani puri wallahs most of the times. And you can see the upper ring, there is an upper ring usually, and the lower ring with the same number of, which is divided into the same number of points. And if you are connecting the points of the upper ring with that of the lower ring and slightly twisting the rings, that's when we get the shape called as a hyperboloid. So this surface shape that we get here is called as a hyperboloid. So two of these hyperboloids when we are using, and each line when it is converted into a kind of teeth, and these two teeth are meshing with each other properly, just the way the teeth of gear are meshing, then that power transmission is going to be possible between two shafts that are neither intersecting nor also are parallel. But of course there's going to be a lot of sliding taking place, much more of sliding taking place when you're comparing it with other kind of gears. So that is one thing that we need to keep in mind. After hyperboloid gears, of course, there are some points mentioned here which you have to go through. If you have any doubts, you can just raise the question in the group and I'll clarify it. Then crossed helical gears, this is another type. This is not actually another type. This is same as the helical gears that we have seen before in the parallel shafts. But in the parallel shafts, I had mentioned that the angles of the two gears need to be the same. Whereas here, when you are talking about the crossed helical gears, the axes are not parallel here, and still we can use the same helical gears but engaged in a different way, so that the transmission of power is possible along shafts which are neither parallel nor intersecting, so they are skewed in a way. So here in the diagrams you can see in the first case it is exactly the helical gear which are connecting to parallel shafts, whereas here in this diagram you can see that the shafts are perpendicular to each other when you are seeing in the top view, whereas they are not intersecting, and still we are using the helical gears. The right side in the diagram it shows the meshing, how it happens with them. And the last type of skew shafts are the worm gears. The worm gears are basically they basically have their axis, the rotational axis are perpendicular to each other when you are seeing in the top view, whereas they are not similar to the helical gears that we see on here. And they are called as self-locking gears because the rotation of this large spur gear is not at all possible, and there's only one way to control this gear, and that is by way of controlling this smaller screw which we see at the top, and that's actually called as a worm. And you can see that when the upper worm is actually rotating, you can see its motion is very similar to a worm which is lifting, which has myriads of legs, and each leg it just lifts from one point and it just moves ahead, and that's basically why it is called as a worm gear. And there are some additional points here which I have mentioned, and there are 3 types of this gear, and you can see them here. The first type is what you see here in the diagram. In this particular type, the worm is straight, as well as the big annular wheel that you see, that is also straight. That's what is happening in the first case. So you can see here at this point this cross section is straight, whereas here as well this line is straight. Whereas here in the second case we can see here this line is straight, but here what we see it is slightly curved. You can see at the bottom this is more clearly shown. So this part is actually surrounding the screw. And in the third case you can see both of these curves, both the worm as well as the big gear, they are both encircling each other. So this part is also not straight and it is engulfing, and this part here for the another wheel you see in the side view is also trying to encircle the worm gear. You can easily make out what are the differences between this, what are the advantages of having these different designs. But in the first case there is going to be very little engagement, and high loads cannot be supported. In the second case there is slightly more contact, and hence more transmission can happen, more load bearing capacity is going to be present in the second type, and the third one has maximum load bearing capacity. But when you're seeing about the efficiency of the gears, the efficiency is going down as we proceed from the left type to the right type, because as there is more the surface contact, because this is going to be naturally the kind of friction that we have here is going to be lubrication type of friction, and viscous forces are going to be coming into action, and that will effectively increase the kind of friction that is experienced by these parts. And when we see the third type has maximum amount of friction generated due to more surface rubbing action, and that is not very good for the gear. Lastly, we have something called as Hypoid Gears. These gears are used in end portion of the hyperbolide. They look like spiral gears but are actually parts of hyperbolide. A hypoid pinion is larger and stronger than the spiral bevel gears, smooth and quiet in action. I was actually not able to get a diagram for this. In case I'm able to get it, I'll just put it in the notes, and you can just stay in contact with the notes to check out what are the additionals taking place in the notes. So that's it for in this video, and the next video will be taking up the nomenclature of the Spur Gears. So stay tuned to the channel to get that. Thank you.